I propose to do in the 4 sessions that I've been given is to talk about, on this first session, 5 anomalies which current science can't explain, the speed of light being one of them. In the second session, which will be the first session tomorrow, I propose to talk about the solution to this problem. There is one thing which links all of these 5 anomalies together, this discrepant data. There's one fact which science needs to plug in, and once this fact is plugged in, you get an entirely different scenario for the order that we see around us. And then on the second lecture tomorrow, I'll be talking about the astronomical implications of this work, and then in the third session tomorrow, the geological implications. And John has given quite an interesting introduction to the geological side of things here tonight. So let's get down to work. 5 anomalies that require an explanation. I'm old enough to remember the time when the Big Bang was not the leading cosmological model. Rather, the steady-state theory under Hoyle, Bondi and Gold was the leading explanation for all the phenomena that we see out in the cosmos. The steady-state theory fell around about 1960, actually just after 1963, when the discovery of quasars occurred. Quasars are hyperluminous, ultra-active centres of galaxies that we see right at the frontiers of the cosmos. The steady-state theory said that the cosmos looked basically the same at any point in time in the past or in the futures. And the interesting thing was quasars denied that proposition, because quasars was something acting uniquely out in the frontiers of the cosmos that were not acting close in. So quasar numbers increase towards the frontiers of the universe, and so does their brilliance. So the universe looked different back in the past. So quasars prove that the universe changes with time, and this went against the steady-state model and supported the Big Bang. Swift on the heels of the discovery of quasars, another development occurred which proved fatal to the steady-state theory. The originator of the Big Bang, George Gamow, predicted in 1949 that fossil radiation as an echo of the Big Bang should be found, and that fossil radiation should be around about 50 degrees Kelvin, 50 degrees above absolute zero. In 1965, Arno Penzias and Robert Wilson found the microwave radiation background, and they found this at a temperature of 3 degrees Kelvin. Even though the temperature of the radiation was much lower than predicted, this background radiation was accepted as proof that the cosmos initially had a super hot, super dense state and was then expanded out. Because the Bible mentions 12 times that God created the heavens and then stretched them out, this discovery caused Penzias to accept the Hebrew Scriptures. He said that this result was expected from the book of Genesis, the Psalms, the Bible as a whole. And because the Big Bang appeared too close to the biblical creation for scientific comfort, the steady state had been initially accepted. Indeed, in 1985, the Cambridge Atlas of Astronomy on page 381 and 384 said that the Big Bang was the theory of sudden creation. Furthermore, on the 10th of August 1989, the editor of the journal Nature, the prestigious scientific journal Nature, Dr. John Maddox, wrote an article entitled "Down with the Big Bang." And he said the similarity gave credibility to creationists, and he declared the Big Bang therefore was philosophically unacceptable. And he said that within the next 10 years he expected that the Big Bang would be superseded. Well, that decade has passed since Maddox made his statement, and the Big Bang is still with us. But there are some problems. The Hubble Space Telescope has uncovered some new data at the frontiers of the cosmos, which has overturned many ideas. And as a consequence of this, the Big Bang math has had to have several more parameters added to it to try and get their equations to work properly and to get agreement between theory and data. In addition, some observations have shown that the standard formula breaks down at the frontiers of the cosmos, and there's a different formula operating from there on. So you have all of these problems. These results are warning signs that a theory is in trouble. And so a reassessment is needed for Big Bang modelling. Now, the whole idea of the Big Bang started in the late 1920s with the discovery of the red shift of light from distant galaxies. Now, some of you may not be familiar with what I'm talking about with the red shift, so I'll take a moment to explain. If you take light from the sun and pass it through a prism, it breaks up into the 7 rainbow colours. And if you have a look at this rainbow spectrum in detail, expand it out and have a look at it through suitable instruments, you find on the coloured spectrum, you find dark lines. And each of these dark lines has come as a distinct pattern from a given element. So the elements that are present in the sun leave these dark lines, these regular patterns on the spectrum of the sun. And so we know what the elements are in the sun. Each element has this specific pattern of lines. So we know what elements make up the stars, we know what elements make up the galaxies, because we can see these spectral lines from all the stars there. Now here's an important point. The further out you look, the further down towards the red end of the spectrum these dark lines are shifted. It's called the red shift. Thanks, Alan. In this case here, you have some lines from the element calcium. These are shifted progressively further and further down to the red end of the spectrum, the further out you go. And so astronomers look at this red shift of distance, which increases with distance, and they say, all right, there seems to be a standard graph that we can apply, a graph of redshift against distance, which shows that redshift increases with distance in a very precise way. And here's the graph. So if this is the origin of the cosmos back here, and we're down here, that's the form that the redshift graph has. Well, the graph grew steeper as the Hubble Space Telescope actually shows that the graph grows much steeper at a point up here and goes up more like this. So there's something a little bit wrong with the formula which is used. But what does the graph mean? Basically it means that the further away the galaxy is, the greater the redshift is. And we need to explain why there is a red shift. Astronomers thought initially that this red shift was due to a Doppler effect with galaxies racing away from us. As the galaxies race away, they said the light waves are being stretched as a result of this motion. Now you're familiar with this sort of principle. As a police car goes past you blowing a siren, the pitch of the siren drops. And so that as the car is moving away from you, the pitch drops. As a galaxy is moving away, the pitch of light drops. So it's moved towards the red end of the spectrum. It's called a Doppler shift. And if the Doppler approach is followed, this implied that the cosmos was expanding faster at greater distances. Therefore, the cosmos expanded faster in the past and slowed down by gravitational forces. Edwin Hubble, of Hubble Space Telescope fame, questioned this explanation when it was proposed back in 1929. The problem was that the red shift are simply numbers, but they are now expressing it in terms of a velocity, something of a speed of recession. And to get a velocity out of a pure number, you need to multiply it by something which has velocity. And so they're actually doing a bit of jiggery-pokery here. And Hubble thought in fact he was not sure that there was necessarily a connection. He thought there might be some other explanation, and there have always been some astronomers who have questioned this explanation, this expansion explanation, even though the majority have accepted it. And while most agreed that this was the interpretation of the redshift, another approach to the data with the same result was in fact offered. A new mathematical basis for the expanding universe was formulated by Lemaitre in 1931 as an extension to relativity. Einstein's approach was that you had static space-time and the galaxies were moving through it. But there's a problem here. If these galaxies are moving at such great speeds right at the top of the graph there, they're moving at speeds close to the speed of light, and the galaxies would be torn apart and disrupted. Therefore, it was proposed that by Friedman and Lemaitre that the fabric of space-time itself was expanding, and that as light waves travelled through this expanding space, their wavelengths were stretched, and this is how you got the redshift. Therefore, the more time light was spending in transit, the more it was stretched and the redder it became. And this is the approach accepted today by many astronomers, but it's not all, because in the popular press you often find that the Doppler explanation is promoted, and even some professionals still hold to it. The problem is that the new Hubble Space Telescope results only work if the expansion rate has increased with time, not decreased. And so neither approach predicted this result initially. And so this new development had to be factored in to the equations for the redshift. But either way, the redshift was the foundation on which the Big Bang was built. But there's another problem to both approaches which surfaced in 1976 and has been with us ever since. Both approaches predict that there should be a smooth change in velocity as you go out, just like a car accelerating down a highway. As a car accelerates, the velocity smoothly builds up, and you would expect then that as the galaxies were moving away, this expansion of space or whatever, you would expect a smooth increase in velocity as you went out in distance. The redshift doesn't do this. Instead, it appears to go in jumps, like a series of steps and stairs. The word that is used is the word quantized. The redshift measurements seem to stay the same over some distance, then take a jump up, stay the same, jump up, stay the same, then jump up again. Naturally, this finding was highly disputed back in 1976, but more measurements have been made, and the more measurements that are made, the more it appears that this effect must be genuine. It was started by William Tift, a professional astronomer in Arizona, but astronomers were aghast at this development because it meant that the whole basis on which the Big Bang was built was falling to pieces. And they expected that it would be easy enough to disprove the quantization of the redshift by simply getting more measurements. In 1981, an extensive redshift survey was published by Fisher and Tully. Interestingly, the redshifts did not appear to be clumped in the way that Tift had said that they were, and astronomers heaved a sigh of relief and said, well, the fun is over. Then it was discovered in 1984 that if the motion of the sun, moon and planets through space, if that motion, which gives you a genuine Doppler motion, if that motion is taken away from all of your redshift measurements, you then end up with quantized redshift globally across the whole sky. In 1985, two astronomers, Salentic and Arp, who were not expecting it, found it turning up in their study of 260 galaxies. In the mid-1990s, Guthrie and Napier specifically set out in Edinburgh, at the Edinburgh Observatory, to disprove this redshift quantization. And instead, they ended up supporting it with a cluster of 399 observations. In 1998, one courageous astronomer wrote, "One can see at a glance how accurately the troughs and peaks of the redshift march metronomically outwards from 0 to over 2,000 kilometres per second." Wow. Well, all of this has been disputed. Astronomers are still arguing, and this has resulted in a number of rather nasty jokes against astronomers. For example, one which has been going the rounds goes something like this. The astronomer at a university races into the head mathematician's office and says, "I've just made a wonderful mathematical discovery." "Oh," said the mathematician sceptically, "what is it?" "Oh," said the astronomer, "all odd numbers are prime. 1's an odd number and it's prime. 3's an odd number and it's prime. 5's an odd number and it's prime. 7's an odd number and it's a prime number. 11's an odd number and it's prime. 13's an odd number and it's prime." Just a minute," said the mathematician. "What about 9? You can divide 9 by 3. "Oh," said the astronomer, "that's just observational error." Well, the problem has continued, and in fact on the 5th and the 7th of May this year, 2003, two abstracts were published in Astrophysics by Morley Bell, who announced further evidence. The second abstract read in part, "Evidence was presented recently suggesting that the galaxy clusters studied by the Hubble Key Project may contain quantized intrinsic redshift components that are related to those reported by Tift. Here we report the results of a similar analysis using 55 spiral and 36 Type 1a supernovae galaxies. We find that even when more objects are included in the sample, there is still clear evidence that the same quantized intrinsic redshifts are present. So this issue, the quantization of the redshift, refuses to go away, even though astronomers are still arguing. It's fatal to both versions of the redshift. Universal expansion, because it requires expansion to go in jumps, and there in fact is evidence that the redshift, the quantized redshift, is not due to a velocity. In the centre of the Virgo cluster of galaxies, right deep in the gravitational potential well, you expect the motion of the galaxies to be high there. As it turns out, the quantized redshift is washed out in the centre of the galaxies. So motion actually destroys the redshift. So the redshift is not due to motion. Okay, well, all this places astronomers with a huge dilemma. Do they want to uphold a model, or do they really want to find out what's going on? Well, these anomalies are a sign of a theory in trouble. For many years, I've been convinced that science can make its most rapid progress by studying those areas of science where there's disagreement between theory and data. In other words, where there are anomalous results. Now, areas where theory and data disagree, and studying this is not designed to make one popular, because you inevitably have to rock the prevailing boat. But it does highlight the areas where current theory needs attention, and the data can't be forced into a mould. And the quantization of the redshift is one of 5 anomalies that the current paradigms cannot explain. But these 5 anomalies are all easily explained if one additional piece is added to the puzzle. I'll list off the 5 anomalies. First of all, there's the quantization of the redshift, which we've just mentioned, plus evidence that a different formula is needed right back there at the frontiers of the cosmos. There's the second one is the decreasing values of the speed of light, which were measured as decreasing up until about 1980. Then there was the increasing values for Planck's constant h. And there was increasing values for atomic masses and synchronous changes in other atomic constants. And fifthly, there's the slowing rate of ticking of atomic clocks. And this comes down into an area which John was beginning to discuss here in the first lecture. These 5 anomalies are all children of the same parent. They all have one thing in common, and we'll be discussing that tomorrow. As Arno Penzias noted, the key is in the Bible, and the topic is going to be the topic of discussion at the next session. But for now, let's refocus our minds on the other 4 anomalies that present theories can't account for. Let's start with the speed of light. And I'm going to use a shorthand, the letter C, when I'm talking about the speed of light. So when I say C is dropping with time, I mean the speed of light is dropping with time. The letter C, ABC. This is the mathematical shorthand which physicists use. Well, in December of 1979, I was given a book from a gift from a friend. It was a book entitled Mysterious Universe, a handbook of astronomical anomalies. My friend knew of my interest in astronomy and my interest in anomalies, and he thought that this 800-page book would be sufficient to keep Barry occupied for a little while. And there I got a surprise. There at the back, near the back of the book, there were listed the measured values of light speed. It was listed and discussed because back in the journals from 1880 to 1940, the measured value of the speed of light was dropping with time. The declining speed of light was a major discussion in the scientific journals in that period, and I was stunned. I hadn't been told about that at high school or university. He was a genuine anomaly. And here's a sample quote from the book by astronomer Emmy J. Guri-de-Bray. This was quoted in the prestigious journal Nature on April the 4th, 1931. Here's what the quote says. If the velocity of light is constant, how is it that invariably, his emphasis, invariably new determinations give values which are lower than the last one obtained? There are 22 coincidences in favour of a decrease of the velocity of light, while there is not a single one against it. I decided to investigate. I expected I'd be able to wrap it up in a couple of weeks. Well, I've had a time problem of my own. Here we are 20 years down the track and it's still going on. It's like an octopus, it reaches out into all areas of science. The behaviour of light has always been a fascination for mankind. From the time of Aristotle to the time of Galileo in 1638, the general scientific opinion was that the speed of light was infinite. Few opposed it. In 1638, Galileo decided to settle the issue by doing experiments with lanterns and shutters on hills miles apart, and they discerned no observable delay in the light travel time. So they still continued to believe that the speed of light was infinite. It was not until 1676 that the Danish astronomer Rømer, in an experiment using Jupiter's moons, presented experimental evidence that the speed of light was fast but finite. This ran counter to the prevailing wisdom and evoked intense opposition, which lasted for half a century. Over 50 years later, Rømer was proven correct. In 1728, the British astronomer Bradley confirmed Rømer's results by a different method, and the opposition finally died down. Light speed, it was generally agreed, was fast but finite. And scientists then continued to measure the speed of light and check its numerical value. And in over 300 years, 16 methods have been used to determine c. And this has given rise to 164 different determinations of its value. Importantly, it's generally true that, with some exceptions, the measured speed of light kept decreasing. It's true even when the same method was used and the same equipment was used by the same observers. There are 17 occasions where the same equipment was used at a later date and gave a lower result. Now, many well-known scientists were involved, Albert Michelson, Simon Newcomb and others, and in general the consistent downward trend in the C values by all methods was evoking scientific comment. In 1886, Simon Newcomb, writing in the journal Nature on May the 13th, commented that the values of C obtained by the methods used around 1740 were consistent, but they placed the value of C 1% higher than in 1880. In 1941, history repeated itself. Physicist R.T. Burge, who kept track of all the values of the atomic constants, spoke of the values of the speed of light obtained by a variety of methods in the mid-1800s, interestingly some of them by Newcomb. Burge acknowledged in the journal Reports on Progress in Physics that, quote, "These older results are entirely consistent among themselves, but their average is nearly 100 kilometres per second greater than that given by the 8 more recent results." Wow. About that time, physicist N.E. Dorsey stated, "As is well known to those acquainted with the several determinations of the velocity of light, the definitive values successively reported have, in general, decreased monotonously." He was not very happy with the situation. So the consistent downward trend in the measured values of C could not be denied, and a great deal of discussion went on in the scientific journals about this. Over 50 articles in one top journal alone. And the discussion was all the more impressive because at the time the speed of light was generally held to be constant. The problem was that if C was in fact changing and was not constant, was anything else changing as well? Other atomic constants had their values reflected in the rate of movement of atomic particles and their associated energies, and these were presumed to be constant as well. But were any of these changing as well? Measurements over time revealed that some seemed constant, others were apparently changing. And if this was true, it was potentially disruptive to the new physics that was developing. One of the key quantities was something called Planck's constant. What it is and what it does we'll talk about in a few minutes. But the letter H is the mathematical shorthand for Planck's constant. But the point is that Planck's constant H was measured as steadily increasing with time. But when H was multiplied by the speed of light c, the result was always a constant, even when checked astronomically. Therefore, with Hc as a constant, if one quantity went up, the other quantity obviously had to go down. So, for example, if Hc equaled 12, this could be 12 times 1, or 6 by 2, or 3 by 4. As one changes, the other changes proportionally, inversely. So this indicated that the measurements of H and C, while C was decreasing, H was increasing directly. As mentioned, Burge was the keeper of the constants. He kept track of the variations in the speed of light and Planck's constant and a lot of the others. And then something strange happened in August of 1941. Burge, in an article on the general physical constants, quote, with special reference to the speed of light, had this introductory paragraph reading in part. Listen to what he said. This article is being written upon request, and at this time upon request. Any belief in the change of the physical constants of nature is fatal to the spirit of science, as science is now understood. That closed the whole discussion. Changing values of the atomic constants was just not on. All constants were declared to be constant. Physics was not going to be sidetracked, and that was that. The issue is now buried, but it was not dead, because the trend in all the atomic data continued. And I started investigating the changing atomic constants, especially light speed, in 1980. The initial incomplete investigations were published in Creation magazine, some with the help of John, starting in 1981. And the ongoing work attracted some attention. In early 1987, I received an invitation to write a major white paper on the atomic constants for internal review at Stanford Research Institute International over in America. This resulted in a 90-page report, The Atomic Constants, Light and Time, co-authored with Trevor Norman. All told, 638 measurements of 12 atomic quantities by 41 different methods were presented. It was published jointly by SRI and Flinders University in South Australia in August of 1987. The data trend was compelling. The Professor of Statistics at Flinders University gave us 100% support and asked us to prepare a seminar on the topic. In December 1987, V.S. Troitsky in Astrophysics and Space Science also mentioned that a decline in C over the lifetime of the cosmos could solve a number of astronomical problems. And then shortly after, all the attacks started to materialise on the report. They were largely fuelled by a poorly written statistical critique that came out of ICR, and it's still circulating today. Interestingly, in the early 1990s, Canadian statistician Alan Montgomery and physicist Lambert Dolphin examined all of the statistical arguments that had been presented and the criticisms, re-examined the data trends in the 1987 report, and published their statistical analysis in a peer-reviewed journal. It has never been refuted. What was their conclusion? Their conclusion was that the statistical analysis supported the data trends outlined in the 1987 report 100%. So there were changes in the speed of light, there were changes in Planck's constant, there were changes in other atomic quantities. So we come back to the actual fact that the speed of light has been measured as slowing. Since then, the variation in C, the speed of light, has become a more respectable idea scientifically. The issue was discussed by Moffat in Canada in the early to mid-1990s, and the matter received media attention in January of 1999 when Ulbricht and Maguigio pointed out that many astronomical problems could be solved if light speed was 10 to the 60th higher at the inception of the cosmos. Can you grasp that? 10 with 60 zeros after it. That much higher at the inception of the cosmos. I have never proposed anything like that. In fact, the data doesn't support it at that high, but that's what they were proposing. And it was proposed that the speed of light then dropped to its present value shortly after because they couldn't get theory to agree with data unless they did that. I had a chat to Dr. Ulbricht in Davis University. Let's see, it would be just over a year ago now. And I asked him why he did that. I said, why didn't you use the concept of conservation of energy? When you do that, you can factor in all of your other constants, and you can get a smooth change in the speed of light over the lifetime of the cosmos. Oh, he said, if we did that, we couldn't achieve the results that we were hoping to achieve. Okay. Well, Professor John Barrow of Cambridge proposed that the speed of light probably has dropped over the lifetime of the universe. Paul Davies gave a similar proposal in 2002 as an answer to some puzzling new data from space. Inevitably, if the speed of light is changing, Einstein's equation E equals mc squared needs some attention. And this aspect of the topic attracted 50 papers which were accepted for journals in the year 2002 alone. In the meantime, what has happened is that the 1987 report has uncovered a basic approach which harmonised all the data trends. The next step was to get to the root causes of what was going on. It's one thing to say that we have the behaviour of the atomic constants and the speed of light linked through conservation of energy, as we showed in the 1987 report. It's quite a different proposition to explain why this was happening. And so to this end, we started checking prospective lines of inquiry. By the mid-1990s, important articles and astronomical observations outlined the general direction that we should take. And I'll talk about them shortly. But it became apparent that there was one major cause behind all of these various effects. And the speed of light was only just one effect, although an important one, and it is not the primary cause of the 5 anomalies. So let's summarise. In summary, the graph of the speed of light behaviour. Here we have the listings by R.T. Burge, the values of the speed of light that he considered accurate. Alan, can we have that up just a little bit higher, please? You can see how there's this drop with time. And all the data listed in the report, all the experimental data is listed in the report, and the Alan Montgomery and Lambert Dolphin stats article is available on the web. The stats article uses several different methods to demonstrate the reality that there is a drop in C over time. So we have, first of all, an anomaly with the redshift, we have an anomaly with the speed of light, and the third anomaly is Planck's constant H. Planck's constant is a way to measure electromagnetic radiation in terms of time and energy. It was defined as a constant, nevertheless, it has been measured as changing. Experimental data collected over a 90-year period shows that H, Planck's constant, is increasing with time. Thank you, Alan. Here's the graph of the officially declared values of H. Data analysis confirms that H has increased systematically. See it climbing up and then tapering off. The experimentally obtained values for H were documented by Norman and Setterfield in the report that we issued there, that H was increasing. As we put out the report for review, one reviewer noted that instrumental resolution, quote, may in part explain the trend in the figures for H, but I admit that such an explanation does not appear to be quantitatively adequate. In 1965, J.H. Sanders in the Fundamental Atomic Constants on page 13, published by Oxford, pointed out, and I quote, the increasing values of H can only be partly accounted for by improvements in instrumental resolution and changes in accepted values of other constants. In other words, they have no explanation for why Planck's constant should be increasing with time. So this increase in H is anomalous. It's something which current theory cannot easily account for. But this is an important clue, as we'll see in the next lecture. The behaviour of H, Planck's constant, is a major clue as to what's happening and why. There may be an extremely good reason why all of these anomalies are occurring. The fourth anomaly is atomic rest masses and the behaviour of atomic particles. And we might have the next one there, Alan. As discussed earlier, some atomic processes are measured as changing, not just H and C. The example that we show here is the atomic masses are measured as increasing with time. This is the official measurements, of the officially declared values of the electron rest mass. Now it's also important that some constants were truly constant. Something, for example, called the de Broglie wavelength. This is the wavelength of an atomic particle in motion. This has remained unchanged with time. So this behaviour of atomic particles needs an explanation in terms of a basic cause. What is going on? Is there some way in which you can harmonise all of this data? We need to know why the constants are doing this. And we discover there's a very viable reason why these quantities are varying. And the fifth and final effect of the one basic cause is the rate of ticking of the atomic clock. And this is where science obtains its expanded timescale of millions and billions of years. But there is evidence that this form of time measurement, called the atomic clock, varies in a way that our own timekeeping does not. It is usual for us to measure time in terms of the time it takes the Earth to go once around the Sun in its orbit, 1 year. That is gravitational, dynamical, or orbital time. Interestingly enough, in Genesis 1:14, we are told that the sun, moon and stars were to be for signs, for seasons, for days and for years. In other words, the sun, moon and stars were to be our timekeepers. Instead, science has gone to the atomic clock and measured time by that process. And as it turns out, the data that we have shows that the atomic clock is slowing down. Dr. Thomas Van Flandern from the US Naval Observatory in Washington studied the run rate of these two clocks. The data that he used was from 1955 to 1984, and he produced evidence that the two clocks were not in harmony with each other. As published in 1984 under the National Bureau of Standards Special Publication 617, Van Flandern is quoted as saying, and I quote, "The number of atomic seconds in a dynamical or orbital interval is becoming fewer. Presumably, if the result has any generality to it, this means that atomic phenomena are slowing down with respect to dynamical or orbital phenomena." Do you get the importance of this? This means that atomic time as measured by atomic processes, went faster in the past compared to orbital time. These two time clocks are therefore not equal to each other. In 1965, John Kowalewski in Metrologia Volume 1, Number 4, said that if these two clocks ticked at a different rate, then Planck's constant as well as atomic frequencies would drift. We've already noted the evidence that Planck's constant is increasing. By contrast, orbital time, the time it takes the Earth to go around the Sun, is still going at a constant rate. In other words, if atomic clocks were ticking faster in the past, it is possible that they could tick off many years in one of our ordinary orbital years. And these conclusions were re-emphasised by comments by Burge, that same gentleman, in Nature in 1934. At a time when the speed of light was measured as changing, but wavelengths of atomic quantities were measured as being unchanged in apparatus which should have picked up any changes, Burge said there's only one logical conclusion. Pardon me. If the value of C is actually changing with time, Burge said, but the value of wavelength in terms of the standard meter shows no corresponding change, then it necessarily follows that the value of every atomic frequency, including atomic clocks, must be changing. Effectively, it means that all atomic frequencies, the number of atomic events per second, is proportional to the speed of light. This is seen from another perspective. All equations describing radioactive decay, and this is how we get our ages in the geological column and for our astronomical objects, all of these equations depend on either the speed of light or on Planck's constant. They either have Planck's constant on the denominator or the speed of light on the numerator. Effectively what it means, since hc is a constant, it effectively means that every atomic equation describing radioactive decay has the speed of light term in its numerator, which means that as the speed of light slows down, all atomic processes are slowing down synchronously. Wow. So all atomic clocks tick at a rate proportional to the speed of light. These processes with radioactive decay and radiometric clocks result in vast ages in astronomy and geology. Therefore, if we discover the mathematical curve that describes the behaviour of the speed of light, that curve will also describe the rate of ticking of the atomic clock. It will also allow a correction to be applied to all of our atomic dates, despite the fact that there's some discrepancies with them. But we can correct these atomic dates to read actual time. As you and I measure time, the time it takes the Earth to go around the Sun once in its orbit. We can then correct atomic dates to read actual time as you and I measure time. And when this aspect of the topic is discussed in the next session. But the interesting thing is that when you do that, the whole of the geological column and the whole of astronomy can be fitted into a biblical time frame. I conclude by summarising the series of 5 anomalies that present theories can't account for. First of all, there's the decreasing values of the speed of light, c. There's the increasing values of Planck's constant h. There's the anomalous behaviour of atoms and atomic particles, with synchronous changes in other atomic constants. There's the slowing rate of ticking of atomic clocks, which affects the rate of radioactive decay. And there's the quantization of the redshift. These 5 anomalies are all children of the same parent. There is one thing which they all have in common. As I mentioned before, the key is in the Bible. We're told in the Scripture 12 times that God created the heavens and stretched them out. Here's the key, and we'll pick up that key in the next session, first thing tomorrow. Thank you very much. Last night we were talking about five anomalies which science couldn't explain, and I think some of you are wondering about the relevance of all this and how you probably fail to realise that what we're doing is something like a detective. We're looking at bits and pieces of evidence and fitting the puzzle together. And these 5 anomalies, as it turns out, have one basic cause, which we'll talk about in a minute. And when this is factored into scientific thinking, it turns out that we've got a young universe, a young solar system and a young Earth, and a recently formed geological column. And this time problem, the problem that we have with the apparent ages of the fossils, the rocks, the stars and so on, is totally resolved as a result of this one additional factor. And in fact, this is a very interesting thing in science. Science only needs one additional fact in any area and you can change the whole way of thinking. And this is because science has not got all truth under its control. God was there when it happened. He has all truth and He's given us His word. And so we therefore go by His word rather than go by what science says. Okay, well, let's refocus our minds now, and we'll have the first overhead. Thanks, Alan. The series of 5 anomalies that present theories can't account for. First of all, as we mentioned last night, there's the decreasing values of the speed of light. And the mathematical shorthand for the speed of light is the letter C, ABC. Then there was the increasing values for Planck's constant H, the letter H. And folk were wondering last night what the relevance of this was going to be, and today we'll find out. Then there was the anomalous behaviour of atoms and atomic particles and synchronous changes in atomic constants, including the behaviour of atomic masses. And then there was the slowing rate of ticking of atomic clocks, which affects the rate of radioactive decay. And then there was the quantization of the red shift. Perhaps that word quantization frightens some of you. It actually means things are going in a steps and stairs fashion instead of in a smooth curve. It's actually going up in a steps and stairs way. So the red shift of light from distant galaxies actually doesn't proceed smoothly. It proceeds in a quantized or steps and stairs fashion. Now, as it turns out, these 5 anomalies are all children of the same parent. They all have one thing in common. It's the energy in space. And as I mentioned before, the key is actually in the Bible. So if we can have our next slide there, Alan. One statement in the Bible occurs 12 times. If it occurred once, it is important enough, but the fact that the Lord mentions it 12 times, we should take careful note. He says, for example, in Isaiah 42:5, that the heavens were stretched out. Thus saith the Lord God, who created the heavens and stretched them out. Or Jeremiah 10:12, God has made the earth by His power. He's established the world by His wisdom and has stretched out the heavens at His discretion. Or Zechariah 12:1, thus saith the Lord who created the heavens, laid the foundation of the earth and formed the spirit of man within him. And interestingly, these statements are always within the context of creation week, and in Hebrew it's always in the past tense. In other words, the action is completed. The first point to note from this is the expansion, the stretching out of the heavens, was completed by the end of creation week. In other words, the heavens are not expanding now. This disagrees with the majority scientific opinion, but is in full agreement with the quantized red shift. We noted in the first lecture that the evidence is that the red shift is not due to the velocity of expansion, of the racing away of galaxies from each other. And in fact, the in the centre of the Virgo cluster of galaxies, where you expect a very much higher speed of movement, right there in the centre of the potential well of gravity, the quantization, the steps and stairs pattern in the redshift, is in fact smeared out. So velocity or movement of galaxies actually smears out the quantization effect. So it means that the redshift is not due to motion. And there are two additional further observational facts which imply that the redshift is not due to the expansion of space. The first fact is that some of the redshift changes, the quantization changes, actually go right through the centres of some galaxies. Now, you wouldn't expect that if you had a whole galaxy moving away. The second fact is that some galaxies have undergone a drop in the redshift by one quantum change over time, over a period of a number of years. When I've compared the measured values of the redshift of a galaxy 15, 20 years ago from what they have today, they notice that the redshift has changed by one quantum number. So the quantized redshift is not due to space expansion, and it's not due to galaxy velocities. So this implies that we must have a static cosmos. So the actual cause of the redshift and how it links in with the energy in space we'll discover shortly. So we've been having a look at this part of the puzzle, and we'll return now to that scriptural statement where God expanded the heavens. How is this the cause of the 5 anomalies that we've just listed off? To understand, we need to dig a bit deeper and to see what was happening as the vacuum of space was stretched out. And Professor Brian Greene said that you might consider the vacuum of space to be a fabric, the fabric of space. Okay, now, when you blow up a balloon, you have invested it with energy. When you have a rubber band like this and stretch it, you've invested it with energy. There's an energy in the tension that's there. You want a proof that there's energy? Look what happens when I let it go. And notice how it flew. It flew very fast to start with, and then it slowed down. So I've just invested the fabric of the rubber band with energy. So when the balloon was blown up or the rubber band was stretched, you have a potential energy involved. Excuse me just one moment. That potential energy has changed to an active or kinetic energy when I let it go. So when God said he stretched out the heavens, if this is what it might be meaning, God not only increased the size of space, he invested it with an enormous amount of potential energy. Well, where is this energy? It's in what we call the vacuum of space. In the same way that there was energy in the fabric of the rubber band. But isn't space empty? Well, no, not really. This discovery was made by physicists around about 1911. Space is full of energy. It's called the zero-point energy, the ZPE, zero-point energy. It's called that because it's there at absolute 0 Kelvin. It's around about minus 273 degrees Celsius or minus 460 degrees Fahrenheit. Robert Matthews in New Scientist for 1995 describes it as follows. The ZPE is a turbulent sea of randomly fluctuating electromagnetic fields or waves. At a macroscopic level, space appears smooth or even featureless. But down at the atomic level, space has been described as the seething vacuum. When you get down to the very small levels of things, space is actually very, very turbulent. Many physicists have calculated the energy in 1 cubic centimetre of the vacuum. And if I might coin a descriptive word, that energy is absolutely ginormous. A conservative calculation has been done, and in my office at home I have a globe, a light globe, which puts out 150 watts. By contrast, the sun radiates at 2 million times greater than that. That is 3.9 by 10 to the 26 watts. In our galaxy, we have something like 100 billion stars. each of them radiating like our sun. With all of those stars shining for 1 million years, that is the amount of energy in 1 cubic centimetre of free space. That is the 0 point energy. It is absolutely ginormous. Now, back in 1911, Max Planck demonstrated that Planck's constant H was a measure of the strength of the ZPE. And this is where the story begins to get interesting, because we talked about the change in Planck's constant last night. And we noted that Planck's constant was actually increasing with time. So as we start putting our clues together, we start thinking perhaps the ZPE, the strength of the ZPE has increased with time as well. Well, this energy has been proven to exist experimentally. When you bring two metal plates very close together in a vacuum, there is a force pushing the plates together. What happens is that the gap between the plates effectively... Not going to matter much, Alan. That's fine, yes. The gap between the plates effectively excludes the longer wavelengths. And these wavelengths which are outside push on the plates, push them together. There's this force pushing them together. And sailors have noticed this a similar effect. When the distance between two boats is less than 1 ocean wavelength apart, the boats get forced together. So the force between the plates, this Casimir force, because it was predicted by Henrik Casimir, the Dutch physicist, back in 1948, was proven to exist experimentally 9 years later by M.J. Sparnay in Philips Labs over in Holland. The force was measured accurately in 1997, January in 1997 by Lamoureux, and in 1998, again in November that year, they achieved an even greater accuracy, about 1%. So the closer the plates are together, the stronger the force. And so at a molecular distance where you have two molecules, you find that there is an attractive force, an apparent attractive force between the molecules tending to push them together. This, in fact, is another expression of the Casimir effect, and it is called van der Waals forces by chemists. Now, the ZPE also causes a noise in electronic circuits, which limits the amplification of signals. Well, the question is, if the ZPE is there, why don't we notice this all-pervasive bath of electromagnetic radiation? Well, for the same reason that you don't notice the 15 pounds per square inch of pressure of our atmosphere on our bodies. It's inside and outside our bodies, it affects all our equipment, and so on. But there's another important puzzle to solve. God said he stretched out the heavens, which gave rise to the ZPE, in the same way that we stretch out the balloon or rubber band. But as we've already noted, Planck's constant H is increasing with time. This means that the ZPE must have also increased with time. And one may well ask why. What is going on? We need two additional pieces of information. The first important component to this puzzle is the role played by turbulence or vorticity. And the relevance will appear in a moment. Let's do another experiment. If you put your hands together in a bath of water and suddenly pull them apart and then lift them out, the expansion results in turbulence in the water. The water swirls around, lots of vortices, very turbulent. But notice something else. There are three stages to this. First of all, there's the vortex formation as you initially pull your hands apart and pull your hands out of the way. But then there is continuing turbulence, the persistence of the turbulence, and then there's the decay of the vorticity. So there's a three-phase process going on here. There's vortex formation, persistence of the turbulence, and decay. You notice the same effects with aircraft. The Boeing 777, the Boeing 777, has a massive vortex formation mechanism. It has a formation mechanism. It has a very long persistence time of over 5 minutes. In fact, the recommendation was that no other aircraft land behind a Boeing 777, for 5 minutes after, otherwise there's a danger of them being overthrown by the turbulence from the plane. So that's the first piece of information. The second piece of information comes from Einstein. As expansion occurs, as the Lord expanded out the heavens, energy is fed into the vacuum. And Einstein demonstrated that matter and energy are interconvertible. The expansion energy formed the smallest possible particles known. They're called Planck particles. And Planck particles come in pairs, positive and negative, because space is electrically neutral. Now, a Planck particle is so small that if an electron was the size of the Golden Gate Bridge, a Planck particle would be smaller than a speck of dust on the bridge. Now, when you have turbulence, as a result of the energy which is fed in by the expansion of the cosmos, these Planck particle pairs are formed. When you have turbulence in a bath of water, you don't produce particles because simply you don't have enough energy to do it. You need a very energetic mechanism. Now please don't confuse Planck particles with Planck's constant. Planck was a very important physicist and his name appeared on both of these things even though they are somewhat different. But let's return to the stretching of space and now try and visualise what's happening. Carl Gibson from the University of California at San Diego noted the role played by turbulence in Planck particle pair formation along with the expansion of the vacuum. At a conference presentation in 2001, he discussed the formation of Planck particle pairs in a cascade resulting from the original expansion condition. Initially, you had the expansion energy producing Planck particle pairs, and he pointed out that once a few Planck particle pairs are formed, rapid expansion will cause spin and separation to occur between these particle pairs and cause intense vorticity. Gibson established that once any Planck particle pairs were present, the energy from the vorticity or the turbulence would produce more Planck particle pairs. In other words, these Planck particle pairs form off the energy of the turbulence. So once the stretching ceases, turbulence continues until all the energy is used up in Planck particle pair formation. So even after the initial expansion has ceased, you have the ongoing formation of these Planck particle pairs. Essentially, the energy from the expansion of the universe goes into the production of these Planck particle pairs. It generates the smallest possible objects in the quantum vacuum. Now, separation and spin of the Planck particle pairs, when you have separation of two electric charges, you have a magnetic field and an electric field as a result of the spin and the separation. And this gave rise to the initial electromagnetic fields of the ZPE, the zero-point energy. But the opposite charges of the Planck particle pairs attract each other. And they combine in a variety of ways. And when these Planck particle pairs combine, they actually give off energy, electromagnetic energy. And this is where the electromagnetic energy of the zero-point energy has come from. As this recombination process proceeds, more electromagnetic energy is produced and the strength of the ZPE builds up. So the energy from the stretching of space during creation week was combined in various ways to form the energy of the zero-point energy from the formation of Planck particle pairs. You have the energy going into the formation of the stretching of space. This energy goes to form the Planck particle pairs, and then the Planck particle pairs recombine to give off the electromagnetic energy of the ZPE. Is that picture fairly plain to you there? So this is the important mechanism whereby the Planck particle pairs gave rise to zero-point energy as a result of recombination. So you have two factors acting here. You have, first of all, turbulence, which is allowing the additional formation of Planck particle pairs, and at the same time you have recombination of these Planck particle pairs giving rise to the ZPE, which is increasing. So you have two factors involved here. So now we have the basic mechanism in place. The potential energy of the stretching became the kinetic energy of the zero-point energy via the production of Planck particle pairs and then their recombination. Well, the question now is, okay, we can account for an increasing ZPE with time by this mechanism. The question now is, how does this relate to light speed and atoms? What has this got to do with the redshift? Why is radioactive decay involved in the atomic clock? Okay, let's deal with light speed first. Another experiment is relevant, and we've all done it at some time and noticed the results. When you put a straw in a glass of water, what happens to the shape of the straw? Anyone? It gets bent. Yeah, it gets bent. Okay, why? Well, because the speed of light is slower in water than it is in air. That's why. The denser the transparent medium, the more atoms per cubic centimetre and the slower light travels. Light speed in diamond, for example, is only about half of that in the vacuum of space. Well, what slows light speed in diamond and water? As a photon of light travels through a diamond or through water, every so often it bumps into an atom. The atom absorbs the photon and takes up a higher energy state or becomes excited momentarily. Then after an extremely short time it re-emits the photon, which goes on its way, and the atom drops back to its normal energy state. As the re-emitted photon goes on its way, eventually it hits another atom. It's absorbed, re-emitted, and goes on its way. And so this absorption and re-emission process takes time. It happens relatively fast, but remember that the speed of light is also very, very fast, and so even a small delay in its progress is going to hinder the time it takes to get from point A to point B. So this absorption and re-emission process slows light photons just like a runner going over hurdles. And re-emission process slows light photons just like a runner going over hurdles. If you're running 100 metres without any hurdles, you can run it pretty fast. But the more hurdles you place in the way, the slower it is going to take to get to the end distance there, the tape that you're running towards. So the situation is essentially similar to a photon travelling in a vacuum. The 0-point energy also affects light speed. The reason is linked with Einstein's famous equation E equals mc squared. We learn from that matter and energy are interconvertible. And what this means in practice is that the 0-point energy allows brief manifestations of what are called virtual particle pairs. You have particles like electrons and positrons forming momentarily and then annihilating. They fluctuate in and out of the vacuum. In fact, they flash in and out of existence, and space is continually filled with this incessant coming and going. So remember, God invested energy into space as he stretched it out. That potential energy has been converted to kinetic or active energy of the ZPE, and that increasing ZPE meant there were more virtual particles in a given distance. And so as the light strikes these virtual particles, it gets absorbed and re-emitted, and it goes on its way. So as the ZPE increases, there are more virtual particles in the way of light as it travels, and so light, effectively, is travelling at a slower rate. So more particles in the line of travel, more time for light, takes more time for light photons to reach their destination. And this is why the measurement of H, Planck's constant, is so important. Planck's constant is a measurement of the strength of the ZPE. The stronger the ZPE, the more virtual particles, the more obstacles or hurdles that light must negotiate. So each time a photon is absorbed and re-emitted, a tiny amount of time is taken up. These tiny amount of times add up and eventually end up measuring as a difference in the speed of light. And this is exactly what experiments have been doing over the last 300 years. Now recall, we've been speaking of Planck's constant increasing at the same time as the speed of light was decreasing. There's a direct link in here. Now you can see why. If the ZPE increases, Planck's constant must increase, but at the same time the speed of light must decrease in inverse proportion. So the speed of light multiplied by Planck's constant is an absolute constant. So all of this occurs because the 0-point energy strength has been increasing with time due to the initial stretching of space in the cosmos and due to turbulence and recombination. The increasing ZPE is the root cause also of changing atomic behaviour, and it solves the redshift anomaly. Let's have a look at atoms. Here's what appears to be happening with atoms in the ZPE. First, there are a number of different views of the atom, but the one that I'm using here is one that we've all learned at school, and is still adequate for most work. Although some models of the atom are more intricate, this model is still good enough to a first approximation. And if the maths work there, you can tweak the mathematics to work in more sophisticated models. The important thing here is that electrons come in groups around the nucleus of their atom. All models agree with that. The link between atomic behaviour and the ZPE was demonstrated in 1987 by Dr. Hal Puthoff of the Institute of Advanced Studies in Austin, Texas. According to classical theory, classical electrodynamics, an electron in an orbit around a proton, as we have here, should be radiating energy. And as it radiates the energy, it should spiral into the nucleus and disappear in a flash of light. But this doesn't happen. Obviously. Matter is here. And according to quantum theory, electrons do not radiate energy or spiral into the nucleus. But that doesn't really explain why it doesn't. Puthoff established that the electron is in dynamic equilibrium. He said, let's calculate the amount of energy that an electron is radiating as it goes around in its orbit according to classical electrical theory, and let's calculate the energy that an electron is receiving from the zero-point energy as it moves in its orbit. And when he did that, it turned out that the loss of energy by the electron is balanced by the energy that it receives from the zero-point energy. In other words, it's like a kid on a swing. Just as the swing starts slowing down, the adult gives the swing another push and keeps the thing going. Puthoff's abstract in May 1987 summarised the situation, and I quote, "The ground state of the hydrogen atom can be precisely defined as resulting from a dynamical equilibrium between radiation emitted due to acceleration of the electron in its ground state orbit and the radiation absorbed from the zero-point fluctuations of the background vacuum electromagnetic field. In other words, the electron can be considered as continually radiating away its energy, but simultaneously absorbing a compensating amount of energy from the zero-point C in which it's immersed." A statement was made by Della Penna summarising the research of several physicists. There's Puthoff, Boyer, Claverie and Diner, and they pointed out, each of these physicists pointed out that there's this balance which gives rise to stable orbits. Here's another helpful comment which may assist your understanding of this. Della Penna said, "If one considers circular orbits only, then one obtains an equilibrium radius of the expected size, namely the Bohr radius for the electron. For smaller distances, the electron absorbs too much energy from the zero-point field and tends to move out, while if it's too far out, it loses energy, it radiates more energy than it receives and tends to fall towards the nucleus." Hal Puthoff commented, "Without the zero-point energy, every atom in the universe would undergo instantaneous radiative collapse." In other words, as God said in his word in Hebrews 1:3 and Colossians 1:17, the whole of the created order is upheld by the word of his own power. This zero-point energy which is there as the result of the stretching of space is upholding the whole atomic system that we are used to. So, all right, with atoms so dependent upon the ZPE, we need to consider the effect of the increasing ZPE. As the ZPE increases, more energy should be available to atoms, and so stable orbits should arise with higher energy values. The results are this as we have a look at the situation. As the ZPE increases and increases and increases in its energy, the atoms will resist this until a threshold of energy is received above which it can respond. It's rather like pushing a glass of water on the table there. I can push it very gently with my finger and it won't move. I have to push after a certain threshold of energy before it will move. I can try and push this podium, and it won't move until I exert something in addition to what I'm trying with just my little toe here. So there's a certain threshold beyond which you have to go before a change will occur. So the zero-point energy is evenly distributed over the cosmos. All atoms access this zero-point energy, and as the zero-point energy increases and increases and increases with time, suddenly a threshold is reached, and all atoms simultaneously take up a new energy state throughout the cosmos. And the light emitted from more energetic atoms is bluer. So this means that atoms are going to emit bluer light, which is bluer with time. So the closer something is to us, the more recent light is emitted and the bluer it will appear. And so the converse of that is also true. The more distant the object is, the older the emitted light, and it's going to appear redder. And this, in fact, is what we're seeing with the redshift. The redshift goes in jumps. This process happens in jumps just like the movement of the glass of water or this podium. Energy is conserved in atomic processes until the additional full quota of energy becomes available. Therefore, as we look back in time, we should see light emitted as being redder in jumps as we go further and further back in time. In other words, the further and further out in space we look, the redder the light should be in jumps. And this is exactly what we see with the quantized redshift. If the ZPE increases with time, then the redshift must decrease with time. In other words, the light becomes bluer. In other words, the redshift is inversely proportional to the strength of the ZPE, just like light speed is. Okay. No one argues that the further we look out in space, with increasing distances, we're also looking back in time. So the further out we look, the further back in time we're going, no matter how fast or slow light travels. Therefore, distance and time are related. And now we have this graph of redshift against distance. But because distance and time are related, we can change that graph to read redshift against time by simply rescaling the distance axis. And a few moments ago we saw that if the ZPE was less, so was the energy of the atom, and the light emitted was redder. Also, we noted that light travelled faster in space when there was a lower ZPE because there were fewer virtual particles. So a high redshift and a high light speed are directly linked. They're the same, they're two children of the same parent. Therefore, on this redshift distance graph, we can substitute light speed for redshift. You have a redshift distance relationship is the same curve as light speed against time. You simply rescale the axes, it's the same curve. And notice the dramatic drop. Dramatic drop here initially, and then it tapers off. It's just like the rubber band behaviour. As we let it go initially, it moves very, very fast and then slows down. Finally, the link between atomic clocks and the biblical timescales. The changing speed of light has important consequences for atomic dating, and creationists have done an excellent job in pointing out the many problems that radiometric dating has. However, there are many concordant dates, and we have a possible explanation here for this with changing speed of light. Equations describing radioactive decay indicate that there is in fact a light speed dependence. For example, many have h, the Planck's constant, in the denominator, and Planck's constant is proportional to 1 over c, and the same result effectively happens when you have c in the numerator of these equations. This is similar for all forms of radioactive decay. Effectively, you have the speed of light term in the numerator of every radioactive decay equation. This was even noticed by Burge back in 1931. He noted that the number of atomic events per second was proportional to the speed of light. So all atomic clocks tick at a rate proportional to the speed of light. These processes result in atomic time. And it's good atomic time. You have an atomic clock ticking off in this fashion. But the problem is that atomic time is behaving in this sort of way as we have on the graph here. So all atomic clocks tick at a rate proportional to the speed of light. So this curve here that we have for redshift against distance is the same as light speed against time, and is the rate of ticking of the atomic clock. It's all the same curve. And so we can use this curve to actually correct atomic time. He said, you're talking about something with a static cosmos. How can you possibly use that formula? That is incorrect. You must not do that. I replied, I said, well, look, first of all, we know that whatever the formula is that the redshift is following, and this is a good approximation, we know that light speed, according to theory, must be following the same curve. He said, that's not good enough. He said, you can't use that formula to describe what is happening. So what's the answer to this? What we need to do is look at the formula for the recombination of Planck particle pairs which gave rise to the 0-point energy. Remember, the redshift behaviour is the inverse of the ZPE behaviour. So as the ZPE increases, the redshift decreases. And importantly, recombination phenomena have a set mathematical form. And also turbulence phenomena have a set mathematical form. When the parameters relating to Planck particle pair recombination is fed into the recombination equation, along with the additional creation of additional Planck particle pairs by turbulence, you find that you get the inverse of the Doppler formula, just as you would expect. This formula, therefore, can be derived from recombination and turbulence without anything to do with velocities or relativity. This formula can be reproduced almost precisely. And so we have here a formula which essentially describes the behaviour of the ZPE, the behaviour of atomic clocks, the behaviour of light speed, the behaviour of Planck's constant, the behaviour of atomic masses, all from the one formula. This is amazing. Well, look at the curve. You've got this dramatic drop to start with. It means light speed travelled really fast at the start. This means that atomic clocks tick very, very fast, ticking off a few million atomic years in one orbital year. But when we start correlating these ancient dates with the speed of light on the redshift curve, we have the consequence that all atomic dates, all of them, can be reduced down to a recent creation time using this curve. In other words, this plus other creationist findings is clear evidence of a young cosmos. Light from the most distant galaxies can get back to Earth in definitely less than 10,000 years. The radiometric ages of stars, planets and the Earth are all less than 10,000 years. The surprise is that geological processes of time have time to work, and it's not just one flood did everything. Other catastrophes are referred to in the Bible and are supported geologically. And in addition, we can relate all astronomical ages and dates to this curve. So we have two things. We have the geological column, and the ages of astronomy of the astronomical objects are all related to this curve. In my next session with you, I'll be talking about astronomy, and then in the elective later in the afternoon, we'll be talking about the geological consequences. Thank you very much.